Okay. I think we will reconvene. I'm trying to wait for my co-chair, but let's get started. So the first talk in this session is invited talk entitled Wenchuan MS 8.0 Earthquake, the Current Velocity Structure and Stress Field from Western Sichuan Seismic Array Observation by Liu, Li, Wang, Guo, and Qi, and the talk is given by Qiyuan Liu.
Okay, next. The Wenchuan earthquake occurred in this May. It's a big event. Which earthquake almost completely destroyed the Yingxiu town. So also the Wenchuan earthquake is a very important event taking place in the boundary between the blocks, Sichuan and the Zhongpan-Ganzi block, which can be attributed to the mountain building process along the Longmingshan Fault. Next. To have a better understanding of the Wenchuan great earthquake, at least we must answer first what is the deformation movement between the Zhongpan-Ganzi block and the Sichuan basin. Second, whether the channel flow really exists in the middle lower crust within the Zhongpan-Ganzi block. Third, how to interpret the specificity of the source rupture process. A key to solve these problems is to study the high-resolution three-dimensional crust velocity structure beneath the blocks mentioned above. Next. So here I show the density movable seismic array which was deployed before the Wenchuan earthquake since October 2006. Totally, it's 297 stations around this area. Now, in this presentation, we want to give some very quickly introduction some of our results in this area to north of the north latitude 29 degree. Here we show this teleseismic events distribution recorded by our movable array up to this June 2008. Totally, there's 690 events with the magnitude larger than the 5.0 at the epicenter distance between 30 degrees to the 90 degrees. Next one. Here is, as an example, I show the receiver function profile along the north latitude of 31 degrees. So we can see this we can roughly see this Sichuan basin have the relatively simple structures, but more complicated in the nearby the Longmingshan Faults and the Zhongpan-Ganzi blocks. Next, please. So also we got this deep structure by using the nonlinear receiver function inversion. So it's the V-form fitting of the receiver function by this technology, in which we also perform this global grid search of the Boltzmann ratios and the Moho discontinuities to get the best, the most optimal V-form fitting. Okay. Here I show also as an example, just show this receiver model along this north latitude of 31 degrees. So we can see this receiver model can be traced very well for each block. Here show the Sichuan basin, this Zhongpan-Ganzi block, and this Chuanbian blocks. Next one, please. To have the either to catch the main features of the deep structure, so we can transfer this receiver model into this color imaging of the crust structure. We can see it's very clear the low velocity layer in the middle lower crust with wedged form. Also, we can see that there's a hard middle lower crust in the strand, beneath the strand basin. So, also we see is the Moho discontinuities have the depth of the 56 kilometers deep in the Songpan-Ganzi block, but also some clear the deformation of the karst in the forend of strand basin. Next one, please. Sorry. Simultaneously, we give the estimation of the Boyson ratio along this porphyry. This high Boyson ratio is consistent with the observation of the low velocity zone within the karst. So this was got by this grid search in the global range. So next, please. Here we show another profile along the east longitude of the 102 degrees. So we can see clear this transition zone or Xianzhihe fault. So it's more deep and more much larger than the crust thickness, about 60 kilometers. But relatively shallow one of the Moho discounted in the Songpan-Ganzi block. But clear that's very relatively hard, this lower crust of the Sichuan basin. Next, please. This figure shows that crust structure along this another northwest direction. So also which the crust this Wenchuan earthquake region. So we can see clear this lower velocity zone in the middle lower crust in the Songpan-Ganzi block. So also we see the clear this deformation of the Sichuan basin. According to our results, we didn't find any phenomena of the subduction of the fallen of Sichuan basin. Next one. So also and give the Moho not Moho, this crust thickness variation over the whole research region. So clear is we show this aftershock relocation by the double diffusion technology. So we can see this aftershock and the manshock have the very good distribution, which was close correlation with the crust thickness variations. So here we also saw the projection of the rupture strip along the Wenchuan fault based on the double district finite fault model made by the Dr. Wang. So a comparison, the two figures, we can see very good correlation between these two results. Next one. Here we show this estimated velocity distribution at the different depths of the 12 kilometers, 18 kilometers, 30 kilometers, and 40 kilometers. So the main very clear feature is the widespread, the lower velocity zone inside of the Songpan-Ganzi block. So also which is controlled very well by this fault in the deep range. So also we see this more relatively more hard middle lower crust in the Sichuan basin. Next one. So maybe this low velocity zone within the Songpan block have some closer relation with the upper mantle. So here I will show the PV velocity perturbation by the using the tomography technique. So we can see clear this low velocity in the upper mantle also is related with the crust in the Songpan Ganz block. This may be a proof which suggests this low velocity zone within the crust have some relation with the low velocity perturbation in the upper mantle. Next slide. So also we're doing some split analysis of the local events. So we found this the time delay of the low velocity and fast S wave is 0.1 to 0.2 seconds. Next one. So then, as you know, it's fast S wave polarization directions with parallel with the maximum compressive stress direction. So we can further estimate, given the estimation of the direction of the stress in the Earth crust. So we can see very clear the features is this stress direction between the Wenchuan earthquake region have very different directions. In the south part, it's have the perpendicular direction almost perpendicular to the Wenchuan fault, but in the north part, it's almost parallel with this track of the Wenchuan fault. Next, please. So maybe this observation is consistent with the source mechanism given by other studies. So this the GPS measurements given by the Dr. Wang of our institute. So we can see this strain rate relative to the Sichuan Yangtze block is decreased from the west direction to the eastern direction. So this may be also a proof this upcrust in the Songpan Ganz block nearby the Wenchuan fault is very hard. So because we have the small strain rate, but we should have the high stress accumulated. Next one. So summarize all of the observation given above in this simple cartoon. So this just show you under this side compression of the Tibet Plateau, this strong deformation in the middle lower crust, but much higher is stress in the upper crust. So should we have the detachment between this upper crust and the middle lower crust, then we can interpret this least shake fault of the Wenchuan area. Next, conclusions. From our observation, we can follow in the conclusions. First, this Chuandian and the Songpan Ganz block, as well as the Chen basin, have the different crustal structure controlled by the deep boundary faults. The Songpan Ganz block is and the Sichuan basin is separated by a collision boundaries. Second, the Songpan Ganz block has a hard upper crust and the middle lower crust with the widespread low velocity zone. This observation is consistent with the high Poisson ratios averaged over the crust. The relative flight Moho discontinuity implies that the low velocity zone within the crust has absorbed the great strain energy. Third, the strain basin has a relatively hard middle-lower crust, which resists eastward movement of the Sungpan-Ganz block, but has been deformed obviously in the fallen. Fourth, the stress field is different on both sides of the Wenchuan earthquake shock nearby the Longmenshan Fault. In the south side, it is the normal pressure, and in the north side, the direction of the maximum compressive stress is nearly parallel with the stress of the Longmenshan Fault. Next one. So some problems maybe still not very clear. First, we need further more detailed studies in the future. First one is under the long-term side pressure of the Tibet Plateau due to the resistance of the strain basin. Large strain energy has been accumulated inside of the Sungpan-Ganz block crust, and its hard of crust should have the great stress accumulations. The detachment between the up and the middle lower crust leads to the thrusters restrict Longmenshan Fault. The Wenchuan great earthquake could be attributed to the sudden release of its long-term accumulated strain and stress energy. Second, rupture process of the Wenchuan great earthquake is controlled by the deep structure nearby the Longmenshan Fault. Third, the widespread lower velocity zone in the Sungpan-Ganz middle lower crust could be related with the lower velocity body in the upper mantle. Its effects should not be ignored completely in the Wenchuan great earthquake studies. Last, the channel flow in the middle lower crust of the Sungpan-Ganz block cannot be confirmed until the more detailed numerical modeling and other geophysical studies, although the widespread low velocity zone has been found in the middle lower crust of the Sungpan-Ganz block. Thank you.
Can I have a very brief question? Just one. Yes.
I think the Moho discontinuity have the very different location in the different blocks. This maybe show this deformation of the crust clearly. And we can see this Sungpan-Ganz block should have the great deformation relative to another two blocks. I think this dynamic situation is completely different for different blocks. It's, particularly this Sungpan-Ganz block should be maybe moved to the northward.
Okay, we have to move on. So the next talk is three-dimensional imaging of Longmenshan Fault using aftershocks of Wenchuan 8.0 earthquake in Sichuan, China by Pei, Su, Zhang, Sun, Toxos, Zhao, and the talk is given by Shen Pei.
Good morning, everyone. My topic is three-dimensional imaging of Norman-San faults using aftershocks of Wenchuan earthquake.
Could you use this one?
that one.
Yeah, okay, want to use this one?
Okay. I saw Okay. The most work of this study have been done when I visited MIT. Thank you. Thank you. So next one. So the Wenchuan earthquake here exists between Sichuan Basin here and the Tibetan Plateau here. So Wenchuan earthquake also exists in north-south.
Sorry,
Okay.
just louder.
Use the big microphone.
Okay. So Wenchuan earthquake also exists in north-south seismic zone. Thank you. Yeah, and the Norman-San fault is here. We want to look into the details of Norman-San fault and try to find what happened there after the earthquake. So then we use the aftershocks data to image the structure of Norman-San fault. The more than 8,000 events were recorded by 63 stations. So we have catalog P arrivals is more than 70,000, and S arrival and S minus P arrival are more than 60,000. The data come from Seismologic Bureau of Sichuan Province. So this map shows the distribution of stations and aftershocks. The red circle means aftershocks, and the triangles are the stations. And then the station along the Norman-San fault here are the temporary stations, and the other are the permanent stations. Next one. So the method we use is a double difference seismic tomography method created by Haijiang Zhang 2003. And here we used his new tomography coda to simultaneously solve for VP, VS, VP, VS ratio and event locations. Next. So we discrete the area into a 3D grid model. The spacing in X direction here is 30 kilometer, and spacing in Y direction is 10 kilometer near the center of the Norman-San fault, and in the margin the spacing is larger. Next. This is the initial model we used, indicated by the red line, and the black line is the Zhuzhao's model. And this is for VP, and this is for VS. The initial VP-VS ratio is 1.71. So use the tomo difference methods, we get the results. We just show some profiles across the main shock in X direction and in Y direction, and the horizontal slice at depths of 40 kilometers. So this is profiles along the red line. This is the VP, and this is the VS, and this is the VP-VS ratio. The blue color here means high velocity, and the color red means low velocity. And the blue line here is the Lumensand main fault, and the other lines are the small faults here. We find the high velocity here is very clear. The Lumensand main fault is a clear boundary between the low velocity in this side and the high velocity in this side. So VS velocity also has the similar pattern with VP. For VP-VS ratio, the Lumensand main fault is also a clear boundary here. Next. Okay, sure. Then we compared the tomography structure with a geologic model. So the PC here, the green color means the Precambrian rocks here. It's a very oldest rock. And the KJT is very young, so it means the edge is a young rock here. And we find the old rock is consistent with a high velocity, and the young rock is consistent with a low velocity. And this is three figures shows the VP-VS and the VP-VS ratio along this direction along the main fault. So we find the high velocity here and here. So VP had a similar pattern with the VS. The VS is also high in this region near the epicenter, and is high also in this region. And the VP-VS is now here and is now in this region. And in the middle, the velocity is low and the ratio is high. The next one. Then we compared the tomography structure with the displacement of SNP. The three figures is displacement SNP obtained by three different groups. So commonly they have two larger displacement center in epicenter and in the other end of the fault. So it's consistent with our tomography structure. So we also have high velocity and low ratio in this region and in this region. So that suggests the fault is knocked before the Wenchuan earthquake and broke after the earthquake. Next. This is a horizontal slice at depths of 40 kilometers. We also find the high velocity in this region and in this region. The VS is similar, the high here and here. And the VP-VS ratio is now in this region and in this region. So the black line is in the fault, and the red line is a rupture in the surface. And the Nomensen fault is also a corneal boundary here. The aftershocks in this part is about 10 kilometers far from the fault in the surface, which is consistent with reverse fault here. And in this part, the aftershocks is very near with surface rupture. That means the fault is vertical and consistent with with the geologic strike slip fault here. So next. So we also compared the tomography structure with the geologic model. We also find the pre-Cambrian rocks. All rocks here have a high velocity, and we also find in this part the rock is also pre-Cambrian and also has a high velocity here. Next. So this is a checkboard test to test our resolution of a result. So we find near the center of the fault, the resolution is good. And VP and VS and VP-VS ratio have a similar resolution with VP. So conclusions. The first Nomensen main fault is a corneal boundary in velocity and VP-VS ratio. The second is the velocity model is well consistent with the geologic model. The old rocks have high velocity and the young rocks have low velocity. And the third is a large displacement of the source rupture looks like having a high velocity. That suggests knocks there before the Wenchuan earthquake and broke after Wenchuan earthquake. So, thank you.
We have time for a couple questions.
Yes, the aftershocks seem to be widely distributed with respect to the fault line. Is that because they really are distributed, or is it because the relocations need to be refined?
Because the fault is a reverse fault, so the aftershocks will be the broadband width, so about 10 kilometers wide. Okay.
In that southern part near the hypocenter, do you think what is the dip of that aftershock zone?
The depth of the main shock is 14 kilometers, and then the aftershocks depth of the aftershocks is most exists about 20 kilometers. So it's a range. It's a belt.
Okay, we will move on. The next talk is entitled Cold Seismic Rupture Distribution of 2008 Wenchuan China Earthquake Inferred from GPS and INSAR measurements, and by Shen Wang, Sun Wang, Zhang Gang, Zheng Wang, and very mouthful, isn't it? And the talk is given by Chen Kansen.
Good morning, everyone. Okay, let's go to next. To study the coseismic deformation of the Wenchuan earthquake, we like to first address a few scientific questions. Number one, of course, we like to figure out the fault rupture geometry and the fault rupture distribution. And based on that, we like to gain more understanding on the mechanisms which control the fault rupture distribution. And also, we would like to know whether we can understand better the regional deformation mechanism and what kind of roles the Lumenshan fault plays in accommodating the regional tectonic deformation. Next. And this figure shows you the regional tectonics of the Lumenshan fault and the Wenchuan coseismic rupture. And the red lines are the surface, the rupture traces of this earthquake. From that, we know that it's pretty complex because it ruptured the two faults simultaneously. One of them is the Beichuan-Yingxiu fault, which has been ruptured for something like 240 kilometers long. And the second one is the Guanxian-Jiangyou fault, which is parallel to the Beichuan-Yingxiu fault and has a surface rupture something like 30 kilometers long. Next. And to invert for the coseismic rupture, we use two data sets. First is the GPS. This figure shows you the red arrows, the GPS derived the horizontal coseismic displacement vector, and the green ones give you the vertical coseismic displacement vectors. The next one. Another important data set is from INSAR. For that, we have two INSAR data sets. The first one is from the ALOS PALSAR satellite data of L-band from Japan. And this data set, because of its long the wavelengths, it provides very good data coverage on both sides of the fault. And we use the ROI-PAC software to process data with ALOS, the extension coded by Sandwell et al. And the figure shows here, actually we have two because we have 8 frames. Now to get overlap with each other, we plot them in separate two figures. And from that result, the number one impression is that we do have a very good spatial coverage for the whole coseismic rupture region. And also we noted that the data set also has the weakness because it's vulnerable to the ionosphere disturbance. So we do see some kind of fairly strong long-range interferogram the patterns which existed in the intermediate and far field. Because of no reasonable coseismic deformation could really explain such data, we simply clipped out part of the data sets which are outlined by those the black frames as indicated. The next, as indicated by those arrows. Okay, next. And besides the ALOS data, we also have the MSAT data from ISAR, which shows as the right panel, and it has a pretty nice the feature, but only within the footwall side of the fault. And so together with the ALOS and MSI and the GPS, we do have a pretty complete geodetic data set. Next. So to do the geodetic inversion, first we need to devise a fault model. We have a few assumptions. Number one is that the rupture breaks to the surface. Number two, that we assume the deep angle is constant along down deep and varies continuously along strike. And this is particularly necessary because during the data inversion, we do find that the deeping angle plays a very important role in fitting the data. And we allow that to vary laterally, except at continuously, except at one spot near Nanba, which here, because the aftershock data suggests that you need the lateral jump across this spot. So we do allow a lateral jump of the deep angle across this spot. The next. So these red arrows indicate the deep angle, the parameters we assign for this fault model, which also are included in the inversion. No, not done yet. Yeah. So the interval inversion, we first impose first order smoothing on the fault slip distribution, and then we perform a Newtonian nonlinear inversion in an iterative the procedure to invert for the fault slip distribution and for the inside phase data offset across the fault, and also the fault deep angles at 6 junction spots as shown in this figure. Next. To construct such a fault model, we first need to identify the surface rupture, and so that we can define the top layer of our coseismic slip model. And we use the ALOS data to get the range and the azimuth, the offsets, which demonstrate clearly the surface offsets in those figures. Next. So after something like 30 rounds of the iterative inversion, we finally got the solution converged. And the top left panel shows you the data, and the top right panel gives you the model predicted inside measurements. And the bottom panel shows you the posterior residual. The first glance of the top two figures give you a pretty general impression about fitting, and I have to say it's pretty good, and pretty much recover the general feature. And although that we do find in the residual field pretty strong ionosphere disturbance effect, which, as I said earlier, we have clip out this part of the data. Next. And so about the model results, this diagram shows you the slip distribution in the entire fault plan. And the first very promising feature is that we do see two very strong peaks near the surface. One is near the town Beichuan, and the other near the city, the Yingxiu. And the one near Yingxiu is something like 5.8 meter reverse slip, and the one near Beichuan is like 5.2 meters the reverse slip plus 4.8 dextral slip. And we also found like 4.6 dextral slip near Namba and like 3 meter near Qingchuan. In terms of the Guanxian Jiangyou fault, and we moved it away from the original spot to avoid overlap, and it shows something like up to 2 meters the reverse slip. And also we placed horizontal fault patch at the southwest end of the surface, the co-seismic rupture fault model, and we found that the data do request something like up to 2 meters of the reverse slip in this horizontal patch. Okay, next. In terms of the fault geometry, we found that the deep angle does vary along strike from relatively shallow 43 degree at the southwest end, which increases progressively toward the northeast, and it has something like 6 degree jump near Namba and reaches vertical at the northeast end. Next. And here gives you a comparison between the geological findings by field geology, and the left panel shows the comparison between the field geology shown as the blue lines, and our model prediction is shown as the brown columns. In terms of the thrust component, the two do have a very good agreement in terms of the general feature, but we do admit that we cannot reproduce some high-frequency changes, only the low-frequency, the general features. And the fitting for the dextral component is not as good as the thrust component, but still it has a general good fitting for the feature. Next. Now, since we are seeing these two very prominent peaks, one question is we have to ask is why the slip peaks near Yingxiu and Beichuan, and where we know that also the greatest fatalities and property damages are also found. Next. Okay. We know that the both places are near the fault junctions and might be fault barriers. And that means they would rarely break during the earthquake unless the stress buildup were high enough and the dynamic triggering is strong enough. And if we look at the fault geometry, that the Guanxian Jiangyou fault the close up at both the places. So the fault geometry near the two peaks are quite complex. For example, there is the Xiaoyudong fault, which strikes northwest, just conjugate fault to these two faults. So from the fault geometry, we recognize they must be, or they are likely fault barriers. Next. And so another question we like to address, what factors control the fault geometry and the faulting mechanisms. Next. And to answer that question, we devised the regional block motion model using GPS velocity data, updated using the most the recent GPS measurements. And the purpose of that is to find whether there need to have motion difference between the southwest Longwenshan block and the northeast Longwenshan block. Next. Oh, it's, yeah. To answer the question, we do find yes, they do move differently with respect to the Sichuan Basin, for example, the northeast Wenchuan, the block doesn't have significant shortening and less than a millimeter dextral motion, but for the southwest Wenchuan, it has 1.7 dextral motion and 1.4 the shortening. These patterns are kind of consistent with the co-seismic deformation pattern. Next. Okay, here are some questions. Probably I will not read it, and I will leave there if there is time for questions.
Yeah.
Yep.
So can we have one very brief question, please?
You mentioned like there are two patches of last day, the jump and fall, but we have more than two jump and fall. Why we have last day and other jump?
Yeah, can we go back to the default model?
Can you repeat the
Okay.
Okay. And the question is, he said that I had only two junctions of the fault, but in reality we had more, probably based on geology, right? And in the fault model, actually, if we go back, that I do have more than two the junctions, and in this we have Nanba and Beichuan and near Yingxiu. So these three, we believe, are the three major ones. Right now, the geodetic data can only resolve these three.
Okay, we have to move on. So the next talk is entitled Kinematic Seismic Sleep Model for the 12 May 2008 Wenchuan Beichuan MW 7.9 earthquake in Sichuan, China, from joint inversion of ALOS, envisaged and teleseismic data by Fielding, Sladen, Lee, Ryder, and Bergman, and the talk is given by Eric Fielden.
Well, Eric is climbing on the podium. If Dr. Senthil Kumar is in the audience, could he please come forward? Please use this one. The other one is fascinating.
Go back. Hello, yes. This is a cooperative effort between me and people in the Tectonics Observatory at Caltech. Anthony Sladen has done most of the seismic inversion work, also Jean-Philippe Avouac. Shenhong Li has contributed a lot of the INSAR analysis, also looked at the geometry issues, and Isabel Ryder and Roland Bergman at Berkeley have also been involved greatly. So this earthquake has struck at the very eastern edge of Tibet, on the very steep topographic boundary between Tibet and the Sichuan Basin. At the next slide shows where the earthquake hit. The next slide shows a little more detail in the topographic data from the SRTM. We can see this very steep mountain front going from about 500 meters or less above sea level to nearly 5,000 meters in a very extremely short distance. The surface ruptures extended about 250 kilometers along strike, and the epicenter is near the southwest end. This is the NEIC epicenter. And of course, the very sad thing about this earthquake is that there were at least 70,000 people killed. Next. And Alex Densmore mapped, and colleagues published a paper last year looking at geomorphic analysis of the area, both in the field and on topographic data. He identified the two major active faults were the Beichuan fault here in the very steep part of the mountain front, and a secondary fault out in the basin called the Penguin Fault. Next. Okay. This displayed okay earlier. I'm not sure what the problem is. Well, if you could see this image, it's a map of the range offsets measured from the ALOS PALSAR data. It's very similar to the analysis that Jing Kang just showed. This is a little bit more detailed map showing that we can look at the discontinuities in the pixel offset measurements and locate where the fault ruptures occurred. The red line on the previous map was derived from these ALOS range offsets these, because in the range direction, the measurements are the same line of sight displacements that we measure with INSAR. So it's a combination of vertical and horizontal motion. The look angle for the ALOS is to the east, to the northeast, with an angle of about 38 degrees from the vertical. The ALOS PALSAR, the azimuth offsets, the along track offsets, are heavily contaminated by the ionosphere or satellite motion artifacts that Jing Kang mentioned earlier a little bit in the previous talk. So those aren't very usable. There is also a very steep, there's a very sharp discontinuity here, which indicates that there's a small scale northwest striking fault here that has a left lateral slip in its detail. So going on to the next slide. This is the combination of the interferometry data from 7 of the tracks. We haven't yet been able to get the data from the 8th track that Jing Kang showed. It seems that the Alaska SAR facility has trouble processing this data for some reason. But these 6 tracks cover the main part of the rupture, and then this track 470 up here covers the deformation off the end, and 477 over here also covers the extended deformation in the southwest side. We lose coherence in the area of very steep topography along the mountain front, and also where there's extensive landslides, especially up in this area where the surface has been disrupted and there's no longer any coherence of the surface material. There's also, as you can see from here to here, there's about 1 meter of very long range phase range change measurement, and we believe this is either due to ionosphere or some kind of satellite motion. Japanese colleagues are saying that it may actually be due to some weird motion within the satellite. But in any case, as Chen Kang mentioned in the last talk, these very long wavelength errors in the data are very large compared to the earthquake deformation at distances farther away. So it's better to cut these out of the inversion, and we've cut out an area where the earthquake deformation is larger than the noise, just using the good signal noise ratio. Next slide. We also processed 3 tracks of ENVISAT strip map interferometry. Track 290 is one that Jing Kang showed, but we also processed track 61 and track 18. Either side. Track 61 especially provides a lot of information about the deformation on the northwest side, and because the look angle on these tracks, which are descending tracks, is towards the west, this gives a very different look angle, which helps to understand the interaction of the vertical and horizontal motions, and be able to separate some of the the components of the deformation. But we also have a problem with coherence. In this part of the fault, there's no coherence in the L-band interferometry. The next slide shows that we also processed the ScanSAR mode data of the Envisat satellite. I've heavily smoothed this data with about a 2-kilometer smoothing, so we are able to get some fringes here, but we haven't been able to use this yet in the inversions. Next. So this is we've done a number of inversions. Zhenong Li is going to be showing in a poster tomorrow inversions solving for the fault geometry. In these particular inversions that I'm showing here, we've assumed a fault geometry with a 33-degree dip on this first segment of the Wenchuan fault projecting to the surface near the Wenchuan fault, and then a 51-degree dip on these two northern segments. The data seems to require a shallower dip on this southern segment to fit the data well, and that's similar to, it could be similar to the Listric geometry that some people have proposed, but we've just using a planar approximation. In addition, there's another fault out here, the Penguin fault. People, Judith Hubbard and John Shaw have done some work on the seismic reflection data in this area and call this the Han Wang fault because of the city of, it's near the city of Han Wang. It's a segment of the Penguin fault system. It runs the whole length of this area, and we had that fault set as a dip of 20 degrees. We've also plotted the co-seismic GPS data, the same data that Zhengkang just showed from the Chinese monitoring network. And this is an animation of the.
So, should I go next?
Go back. Yeah, okay. So you go to the next one. This is an inversion of the GPS data with the teleseismic waveform data. Again, we're using this Chen G code that's been slightly modified at Caltech. Unfortunately, we haven't yet been able to get the code to do the GPS data, the INSAR data, and the teleseismic data together because it runs out of memory, and we're still working on a way to solve that problem. We can do it with a single fault, but with this 5-fault geometry, it doesn't work. So this is a GPS data and teleseismic inversion. It's a kinematic inversion. We had to move the epicenter substantially to match the teleseismic waveforms. So we had to split this first fault into 2 segments with a 8-second delay here from the first segment to the second segment. And we had to move the hypocenter about 15 kilometers to the southwest to have it match the teleseismic waves. And the next slide shows an inversion of the cumulative slip showing the GPS static, quasi-static solutions as they go along. This is not what you would see if you had a continuous GPS station, because these are quasi-static calculations at each time step. But it shows the propagation of the fault slip to the northwest, and total of about 120 seconds of rupture to match the seismic waveforms. And we had this significant amount of slip on this northernmost segment of the Wenchuan fault, and that's consistent but with both the GPS and the INSAR data in this area. We also think that this has a slightly different strike, and that's extending quite a bit to the northeast of where the surface ruptures occurred, and so the slip is primarily at depth. Next slide. This is a cross-section through that same slip model. This is that first slip patch. Fairly small amount of slip on this, and then a major, somewhat of a delay here. Seems to best fit the waveform data, and then a much greater amount of slip. This particular solution has a very small amount of smoothing, so it has extreme amounts of slip in a few patches, but so don't worry about the exact magnitude of slip. We can say that there's at least 5 to 10 meters of slip in this area here. This is primarily thrust motion in the first 20 to 30 seconds. It's also thrust motion over in here, starting to rotate into strike slip. Up here near Wenchuan, it's now primarily strike slip motion, and the northern part of the fault is all strike slip. This Han Wang fault slip we constrained to be nearly pure thrust based on the what we've viewed on the radar image offsets. And this extreme damage and heavy landsliding area is near Wenchuan and to the northeast is consistent with this very high amount of slip in this area. So in conclusion, the Wenchuan fault system was the main rupture. It has a shallower slip on the southwest end of the rupture with primarily thrust motion in the first 30 seconds or so. And then the slip rotated to more right lateral, nearly pure right lateral to the northeast. We can't distinguish whether there was two separate faults or rotation of slip on a single fault, but there doesn't seem to be any time delay during this rotation period, so it could well be on one fault and may relate to the fault geometry changing from the shallower dip to the southwest to the steeper dip to the northeast. The Han Wang fault had large thrust motion. There was also a large amount of slip near this town of Xiaoyudong, which had lateral motion. Joint inversions with the geodetic data and teleseismic data combine the time and space constraints to give a more complete picture on the kinematics of the rupture. And we need this angle diversity from the INSAR to understand this complex rupture. And the SAR pixel offsets are what we use to measure the surface ruptures. Thank you.
We have time for a couple questions. Okay, yes, in the back.
Yes, she asked why we had to move the hypocenter location by 15 kilometers from the NEIC location. Well, for one, the NEIC location has a large uncertainty. So I would love to have a better hypocenter location for the main shock if somebody here has a much better location than the NEIC location. Perhaps the MIT group has a better location for the hypocenter. But in addition, because there was a very large amount of slip after 30 seconds, the hypocenter has to be some distance away from that in order to have enough time for that slip to without having an unreasonably slow rupture velocity. It doesn't depend on the fault geometry. It's the NEIC hypocenter is very close to the very high amount of slip, which didn't start until about 20 seconds into the earthquake. So unless there's an extremely slow rupture velocity, the hypocenter has to be further away from that area of high slip. And the area of high slip is constrained by the INSAR and GPS data. So it's the combination of the two data sets together that determines the... I don't remember the moment for this specific model. It's about the same as the CMT moment.
Yeah, we better move on.
Okay, the next presentation is on co-seismic reverse and oblique slip faulting generated by the magnitude 7.9 Wenchuan earthquake. That was the easy part. And it's presented by Xu, Wen, Chen, Yu, Ye, Chen, Li, Klinger, Hubbard, and Shaw. And the talk will be presented by Xu Xiwei.
Okay, let's move to the geology study. To go back to the co-seismic surface ruptures. And since a lot of guys, after the earthquake, a lot of guys go to the epicenter to study the surface ruptures, mapping the surface ruptures. And here I should to mention these three guys helped to use the seismic reflection profiles to reconstruct the three-dimensional seismogenic models. And next. So my topic is just 4 parts. And next, please. I think everyone here knows very well about the aspect parameters. And but I want to remind you to remember this time, just as the bell stopped at this time, just 2 past 28 p.m. And this is a terrible time. And at this moment, terrible earthquakes occurred, and 80,000 guys lost their life just at that time. Next, please. So these earthquakes also gave us a chance to study many problems, and maybe one, why was the disaster so heavy during this earthquake, for this earthquake? And the second one is, does the surface rupture looks like, and it's related to the, can explain why it's so heavy, the disaster. And maybe more is, maybe give an example to make sure which one is more better, or to explain the kinematic models of the Tibetan Plateau. Since you see, at this site, this earthquake occurs along the Longmen-san thrust belt, and this thrust consists of 3 reverse thrust fault, and this earthquake ruptured 2 of them. And next, please. And also, many guys shows at these areas the GPS says a very low strain rate, but the geology study also shows these sections, the middle and the south sections are active. And yeah, thank you. And this map showing the distribution of the earthquake intensity, we can see there are 2 largest intensity located at Beichang. One is here, and another one is here, just the Beichang and Yinxiu. And the intensity reaches 11. So it's really high intensity. So next, please. And we're just showing examples of how heavy disasters, these massive landslides, and covered 4 streets. Several thousand guys covered just by these landslides. Next, please. And this is, we can see this is just this landslides, and also owing to strong ground motions, and around these towns there are a lot of landslides, collapse, and also more important is the earthquake fault just cut this town. Next, please. And this is before the earthquake. So it looks very beautiful, small town in China. Next, please. And when we use the satellite image, and also in the field we map the detail, very detailed, the landslides and the surface rupture zones. This red lines is showing the surface rupture line and cut the whole towns. And also there are a lot of landslides. This is showing before two slides, showing the very large landslides and the collapse here, and also landslide dammed the rivers. So we can explain why so heavy disaster occurred at Peking. It may be main problem is resulted from the co-seismic surface rupturing. And then, next please. Since the large, very strong, strong ground motions, it also induced the landslides and collapse, and also some sites, the liquefations. So that's why heavy disasters occurred at the Peking town. Next, please. Similarly, at the south end of the town, in Xiu town, very similar. The surface ruptures cut the whole town, and also very strong ground motions also recorded just nearby Genda, just at these corners. Also similar, two causes, surface rupturing and strong ground motions. Next, please. So let's look at the surface ruptures. Next, please. So we can see these earthquakes are very special. It ruptured two imbricated reverse fault. One is the Peking fault. Here, this one. And another one is a range front fault. Just here. And another one is a very small one, is northwest here. Northwest is just 6 kilometers long. It's just showing quite different ruptures. Next, please. And during the field, we find many fault scarps, just as showing this. Every features we find in the field. Maybe several slides we're showing examples. Next, please. This is a thrust scarp. We just find one site, just at the south sections at this site. And since the thrust scarps are not stable, so now if you go to there, you never saw these scarps just collapsed to form next slide, to form the hanging wall collapsed scarp. This is nearby the fault scarp, thrust scarp, and this is also the west of this site. Next, please. And also, very common features is the simple pressure ridges. You can see the cars are still on the different roads. Next, please. Also similar, just the middle of the Peking surface ruptures, also to form very high pressure scarps, and also showing the jagged woods. And you see this vertical, and at the front of the scarp, it dips more. Next, please. And also, at some sites, we can see the back thrust pressures. This is the main scarp, and this is the back thrust scarps. And the next, please. And also showing at least the north of the Peking is showing there are right lateral component showing the dextral pressures, and this is a typical one. The scarps more than 1 meter, and the horizontal one is almost 5 meters. Next, please. And also, quite a special one is we find that just at the Peking city, Peking town, we found the local normal scarp. Also, And on the fault planes, we can find the silicon side almost horizontal. So also showing the north of the town, Beichan town, it have the right lateral component. Next, please. And this is a normal scarps, the bedrock fault planes. Next, please. And also another one is the bending scarp or fault scarp, also showing next. This you see this layers, the terrace layer deposits also bended during the quake, and also this load showing there are 2.4 meters right lateral component. Also at the end of the this rupture, also which can show the land are also folded. Next, please. This is maybe very famous city schools. Teaching, this is teaching buildings. This corner, at this corner, just 3 meters from the scarp. And the scarp is about 1.8 meters high during the earthquake occurred. But these two buildings are still there, and these buildings, almost no cracks around these buildings, but this is many shear cracks here and broken, almost broken. Next, please. So from our surveying in the field, and we find the middle sections, the surface ruptures on the Beichan fault is about 240 kilometers, and another one in front of the range is just 72 kilometers long. But if add this section, short sections, just which is connected with the Xiaoyudong thrust rupture, is 90. And here, northwest section is just 6 kilometers long. And also, this is showing left lateral component on the northwest section. Next, please. And we measured almost many features contributed by the total stations and 3-dimensional laser scanners to get the offset, vertical offset, and the horizontal one. And next several slides showing the measurement results. And this is a 3-dimensional laser measurement maps, and this is scarp. We can show several meters, 4 meters, almost 4 meters. And here, from this, since this is near the Beichan, so it is showing there are right lateral component here, about 3 meters, about 3 or 2 meters, right lateral component. Yeah. Next, please. And north of the Beichan, Pingtong, at this site, it's more clearly there are the right lateral offset. And also, the vertical one are also very obvious. And these two components are almost equal, 1:1. And this is a front, this ruptures the front on the front thrust. Now also we can see almost no horizontal one, but the pure reverse component. Next, please. This is just showing showing the northwest section, so we can see there are left lateral component and also reverse component. And we compacted all the measurements, and we can see this is a vertical offset, and the largest one is just located at the west south sections. It's 6.2 meters high. Next, please. Now, this is the site we measured, about with errors about 0.5 meters. Next, please. And also, there are horizontal ones, and you can see here from this job, at this site is dominated by the reverse component, and north of this job is the horizontal one and the vertical one are almost equal. And we measure the largest horizontal one, just 4.9. Next, please. This is just showing the horizontal one offset, the maximum we measured in the field. Next, please. So, next, please. So, we can reconstruct these three-dimensional structures, two ruptures at the source sections, and measured at the depths. And earthquakes may be originated at the more deeper, and then go up to two branches. But north of the Beichang is just one rupture. Next, please. And and also we can calculate the cluster shortening amount, and maybe the total maximum shortening amount just 9 meters. Okay, please. And we can use these simple models to show in this block horizontal motion are absorbed, transformed into the cluster mountains uplift and the cluster shortening at just along the Longmen-San thrust. So the conclusions, maybe just here. Thanks a lot.
Several question. This was first, sorry.
There are since the maps we have after this map finished, there are several guys went there to see. Also, we find some structures. Yeah, since we haven't measured the offset, since you see many cracks and also especially cracks and landslides covered. So it's very difficult to find the real offset. Yeah, since there are these sections.
I'm sorry we have to move on, but talk later.
So.
Thank you. Next presentation is on precursory signals using satellite and ground data associated with the Wenchuan earthquake of May 12, 2008 by Senthil Kumar, Singh, Senthil Kumar, Gautam Prasad Hattori, Tiger Liu, Part, Slotniki, and Kavatos, and the talk will be presented by Ramesh Singh. Just use this microphone.
Thank you very much. Let me acknowledge my co-authors. Senthil Kumar is from India right now, and Ritesh Gautam is with NASA and GMU. Anup Prasad is with the Chapman University. Dr. Hattori is from Chiba. Tiger Liu is from Taiwan. Michel Perrault is from CNRS, France. And Jack is also from CNRS. And Minas Kafato is from University of Chapman. Right now, I'm at George Mason University. Ever since the Gujarat earthquake, whenever earthquake occurs, people, they try to get the remote sensing satellite data. And also, they would like to see the interferograms. And a Gujarat earthquake, people, they did not find the very good quality of the interferogram. Why? Because of the atmospheric parameters. This is my belief. Okay. And here, I would like to show this. These are the satellite data people, they try to see, and the people, they try to use for the different surface mapping, for the fault geometry, for the epicenter distribution. And my job here is to use all kinds of free satellite data and to see what kind of information we are going to get it. Okay, next please. Okay, see this is a cartoon for the earthquake. Earthquake occurs, 5 kilometers and below. but there are elastic wave emissions, and also we believe that there is the emission of the electronic waves, which propagates within the subsurface and also in the atmosphere. Okay, and the earthquake characteristics vary with respect to magnitude, focal depth, lithology and surroundings, and type of faults. Okay, next please. And see, there are the multi-sensor data available which provides the information about the land, atmosphere, and also the ocean and meteorological parameters. Okay, and since the Gujarat earthquake, we are trying to use all kinds of data. And here, when I included so many co-authors, they are distributed in different countries. They are experts for each individual parameters. Here, I'm trying to integrate the whole parameters and see whether these parameters provide any signature for the precursory signals. Next. Okay, here in this talk, I have tried to use the MOPI data, AIRS, NCEP data, AMSU, SSMI, F14, F15, and GRACE data and Demeter satellite, which was launched by French people. Okay. You can see here, these are the temperatures derived from the AIRS data at different pressure level, and this is the magnitude and the epicenters. And one can see here prior to the earthquake event, there is change in the temperature at a different pressure level. Maximum change occurs near the surface. Okay, next. Again, that was the long window. Here is a shorter window, and one can see the jump in the temperature in the ascending and descending mode. Okay, this is the derived from the AIRS data. Next. Here is the surface skin temperatures, and one can see the change in the surface skin temperatures prior to the earthquake. Yeah, okay, exactly on the 5th and 6th May. Next, please. This is relative humidity derived from AIRS data. And this is for whole, starting from January 1st, 2008 until 29th November 2008. And one can see the lowering down of the relative humidity right on the 5th of May, well in advance prior to the main earthquake. This is the ascending mode, similar to the results we have found in the descending mode also. Okay, next please. So, same thing, the air's relative humidity in ascending and descending mode, one can see the decrease in the relative humidity, and one can see at a different pressure level. Okay, and prior to the main event on the 5th of May, one can see this. Next. And this is the airs measure the different parameters at a different pressure level. And here I'm trying to show the ascending and descending mode, the relative humidity at a different pressure level. On the 5th of May, you can see an enormous change in the relative humidity we have observed in the ascending and descending mode. Next, please. This is the carbon total column, and one can see prior to the earthquake, there is change in the ascending and descending mode, the carbon monoxide. Okay, next. Okay, now I'm trying to show you the SSMI data. SSMI data has a SSMI satellite has 5 frequencies: 19, 22, 37, 85 gigahertz. It measures the brightness temperature in the vertical and horizontal polarization, except the 18 gigahertz, which measures 22 gigahertz, which measures only in the vertical polarization. Okay, we have used F14 and F15 data, and I'm trying to show you the results of the 19 gigahertz in the vertical and horizontal polarization. One can try to see that prior to the earthquake, there is a rise in the brightness temperature. Okay, for the Sichuan earthquake, this rise occurs well in advance. Maximum brightness temperature one can see on 5th of May 2008. Okay. This is again for the 37 gigahertz, similar results we are getting. There is the increase of the brightness temperature prior to the earthquake. Next, please. This is again 85 gigahertz, and it occurs in the horizontal and vertical polarization. Next. Okay, what are the observations from the SSMI data? All the frequencies. The sharp rise in brightness temperature is observed on 7th of May of 2008. And actually, this is not very accurate because the SSMI data, SSMI satellite covered the whole globe in 2 days, but we have averaged for 3 days. Okay, next please. Further from the satellite data, we have tried to analyze some meteorological parameters from the ground observations. And what are the parameters we have analyzed? The wind speed and directions, surface pressure, pressure at the sea level, relative humidity, temperature and dew point visibility. Next, please. And you can see the pressure level. There is a rise in the pressure level. There is a lower rise prior to the earthquake, and this is again there is the rise in the pressure level. Next, please. This is the temperature from the ground observatory, and one can see how it behaves prior to the earthquake, and the rise in visibility also. Next, please. This is again relative humidity, and the ground observation also confirms the drop in the relative humidity and whatever we have found in the satellite data. So this is relative humidity, this is a dew point, and you can see right on the 5th, 6th, there is a drop in the relative humidity. Next, please. This is again rise in the carbon monoxide prior to the earthquake event at a different pressure level, and maximum rise one can see near the Earth's surface. Next, please. This is a D-meter satellite data. D-meter was launched on 29th June 2004, and one can see the change in the total electron density and prior to the earthquake. And this anomalous change occurs on the 5th of May, where we are finding the change in the relative humidity and other parameters. Next, please. This is the this is the GRACE data, and I have taken this GRACE data from the study, Dr. Tiwari, and they are trying to see the GRACE data right from 2002 to 2008, and you can see some anomalous change occurred prior to the earthquake. This is 2007. The limitation of the GRACE data right now is we don't have a daily data, but they have recently released about 10 days data, and so far we have not analyzed, and this I wanted to see how the GRACE data behaves. Okay, so but you can see what War, Bilham, and Tiwari they have done. They have analyzed for the right from the 2002 to 2008, and it gives some signal of the earthquake. Okay, next, please. So now what we believe that there is a strong coupling exists between the land, atmosphere, ionosphere, and which depends on the lithology, depth, subsurface characteristics, land-ocean distance, land cover, hydrological regime, meteorological parameters, skin and surface temperature of land. Okay, and next please. Now each parameter if you analyze, and prior to if you take about 2 weeks window, if you analyze for whole year, then one can see so many peaks for each and every parameter. Okay, and enormous peaks, what you see is, of course, what we believe that this may be related with the earthquake, and also this is also related with the other atmospheric parameters. The main challenge is how to distinguish which peak is associated with the earthquake. Okay, this is the main, and there is a problem to do that because we don't have a very high resolution remote sensing data. Next, please. My model is, if I see all the parameters, I'm trying to say that in first stage, what happens, mostly for the magnitude earthquake 5.5, there is change in the hydrological regime. One can notice from the GRACE data, and also not always. Such changes may give rise to oozing of greenhouse gases, carbon dioxide, carbon monoxide, and other gases. And now, very soon, satellite data can provide such information, and which enhance the skin temperature of the Earth. And people, they are trying to measure the thermal anomalies from the satellite data. In the second stage, the latent heat flux also change, and one may find change in the gravity wave, and also change in the relative humidity, air temperature, and other meteorological parameters, what we have observed. In the third stage, the changes may occur in total electron content and ionospheric perturbations, which is measured from the D-meter satellite. So there is a linkage, and such linkage one should see seriously whether one can get the information about the earthquake precursors. Next, please. So in conclusion, what I would like to say, the satellite and ground data show changes and also complementary nature of various parameters prior to the main event. High spatial and temporal resolution data and monitoring from seismically active regions are required to use these parameters as a reliable precursory signal. I don't think right now we can say that this is reliable. Systematic integrated studies of these parameters are required to understand the linkage of these parameters with the physical mechanism of earthquakes. Okay, I would like to acknowledge thanks to NASA for AIRS, MOPIT, AMSU, SSMI data, and Geology team, and Dr. Perot for the D-meter data, and Dr. Tiwari from NGRI for sharing his GRACE result. Thank you very much. Yes.
A very, very, very quick question and quick answer, please.
When you showed the GRACE data, for example, you saw the increase of mass.
Yeah.
So 2 years or 4 years prior, this earthquake was an account of a reservoir. I wonder whether this mass you can see in the GRACE data, have you tried to look at the meteorological data, which are basically also because of the water lake that is there, which is changing the ecosystem? Have you incorporated this in your analysis?
Okay. The GRACE data is not my data. I took from Dr. Tiwari, and they must be looking also because they are trying to relate with the change in the hydrological regime. Okay.
Okay. Thank you very much.
Thank you.
Next presentation is on identification of seismic disparities of the 2008 Wenchuan earthquake through geomagnetic anomalies by Tsuboi, Yamagishi, Nagao, Nakamura, and the talk will be presented by Seiji Tsuboi. Just use this microphone.
Okay. Thank you. In this presentation, I'd like to introduce brief results of our inversion results for the rupture propagation for the this Wenchuan earthquake. And we'd like to mention that the seismic asperities retrieved from this inversion may be also seen in the geomagnetic field data that was originated by the crustal structure in this region. Okay, next slide, please. So first, I'd like to briefly summarize the inversion or the rupture process of this Wenchuan earthquake. And we assume the single fault in this area, which has basically the same strike and deep angle of the global central CMT solutions, and the rupture length of the fault is about 300 kilometers. And can I have a this is the epicenter, and this is aftershock distribution. So the fault plane solution we assumed is somewhat like this. So next, please. So we use the finite source inversion using the broadband seismograms of the telescopic stations, basically the procedure by Kikuchi and Kawamori. And these are the stations we used for this inversion of the teleseismic broadband stations. And we also use some of the stations that we are operating in this area. And next, please. And these are the comparison of the observation and the synthetics for this inversion, and black traces are the observation, red traces are the synthetics. So we can see that the agreement between the observation and synthetics is good, so our fault model is quite accurate. The next, please. So this summarizes the rupture distribution that we obtained from this inversion. And we should say that strike is in this direction. So the epicenter is here, so rupture propagated to this direction for the northeast. So one of my colleague Nakamura-san plotted in this way, and I found that many rupture distribution study uses reverse strike direction. So I should mention that this is strike is here, so fault rupture from right to left. And anyway, this result is basically the same as those obtained by spiral groups, which means that we have two significant asperities here and here, and the rupture process is about 100 seconds, and this is the fault mechanism in total. The maximum scalar moment is 1.2 10 to 21 Newton meter, so equivalent to moment magnitude is 8.0. Maybe slightly larger, but we think that this is the consistent to other groups. And next, please. We use the spectral element method, which is the numerical technique to calculate the synthetic seismograms on the Earth simulator in Jamstack, to calculate the synthetic seismograms to compare if these synthetics can reproduce the observation. And we use three-dimensional models, and the number of nodes is here, and the accuracy is 5.0 seconds for the synthetics. And next, please. We do not show many seismograms, but just show one example. This is the comparison of the synthetic seismograms and observation for the Antarctic broadband seismogram station that we are operating in Showa station. And in this case, the epicentral distance to this station is more than 100 degrees. So we do not use this station in the inversion for the rupture process. And the first arrival wave is the diffracted P. And anyway, we can see that black traces are the observation and red traces are the synthetic we calculated by using the spectral element method on the simulator. So you can see that the agreement between synthetics and observation is quite good. So we can see that the rupture model that we obtained by inversion is quite accurate. Okay, so next, please. Then we will try to find any other geophysical data that we can compare our strip distribution model obtained by the inversion. And in this study, we chose the magnetic cluster field model, NGDC 720. The NGDC 720 model provides an expansion for the cluster field from spherical harmonic degree 16 to 720. So the shortest wavelength of this model is about 50 kilometers, so which is very short. And because the main field is subtracted in the up to maximum degree 16, so we may say that the cluster field model in this NGDC 720 is originated from the cluster structure of the globe. And we developed a software to convert this cluster field of NGDC model to KML so that we can view the field on the Google Earth. KML is the language that we can use to plot data on the Google Earth. And we have a poster presentation on this software on the Friday afternoon in this meeting. So please visit the poster. So this is the, we calculated the XYZ component of the magnetic field using NGDC 720 model and calculated the total intensity field from this model. And this is the total intensity field model of NGDC 720 in this region. And blue color illustrates the geomagnetic field is total intensity field is small, and the red part is total intensity field is large. And this is the epicenter, and this is the aftershock distribution. So even though we subtracted the main field from this model, still we have some very long wavelengths feature, such as the mountainous region and the basin structure. But we see some small heterogeneity of the anomalies, the geometric field along this fault structure. So we, next please, we try to overlay on this magnetic field model with our slip distribution. In this figure, the height of the bar is proportional to the amount of the slip that we obtained by the inversion. So you see that here there is a large slip, and also we have a large slip here. So we found that there are two basically asperities along the fault. And here is the epicenter, so rupture propagated in northeast direction. And you may see that there is a small magnetic field here, and also you have large magnetic anomaly here and here. So we may say that the location of the asperity might be correspond to the location of the geomagnetic anomaly, which has a large anomaly here and here. So because the maximum order of this model is 720, maybe 15 kilometer is the shortest wavelength. So we know that this feature is rather marginal, but we also expanded the model up to somehow 500 degree or something, and also we found that these anomalies still remain. So we think that these features are quite somewhat robust. So this is clear. So geomagnetic field may be related to the temperature field inside crust. So we try to obtain the Curie point distribution from this geomagnetic data, which is very classical technique to analyze this kind of geomagnetic data. Curie point is the temperature above which the magnetite loses its magnetic property, and we can obtain this kind of Curie point distribution from the spectral analysis of the geomagnetic anomaly on the crust. And if you see this map, we can say, this is the epicenter, and these are the aftershock distribution along the fault. So we can see that there was a small anomaly here, and here the depth of the Curie point is shallow, and here where we have a asperity on the seismic slip, the depth of the Curie point is deep, which means that the temperature along the fault is lower here and here, and the temperature along the fault is higher here, because the Curie point depth is shallow here and deep here and here. So we may say that the temperature distribution can be lower here and higher here in the fault. And next, please. This interpretation may be consistent to the current seismic tomography model recently obtained by Wang et al. 2008. The results are presented in the poster presentation next morning here, S31B. And they obtained the tomographic model in this region by using the travel time anomaly from the local seismic network, and obtained the P wave velocity and S wave velocity and VP-VS distribution along this seismic fault. And this is the distribution model obtained by Yagi. And in this case, strike is here. So rupture started here and propagate to right direction. And their model also shows two significant asperities here and here. And the conclusion of Wang et al. Study is that the higher BP and base velocity corresponds to the seismic asperity here and here, and also corresponds to here. So they suggest that temperature in this area might be lower. And also there is a slow velocity anomaly here, which is just the southwest of the epicenter. And this location can be characterized by the lower geomagnetic anomaly that was shown in the NGDC model that we showed before. Okay, so in summary, we have inverted the seismic slip distribution for this earthquake using the teleseismic broadband seismic elements. And seismic asperity on the fault coincide with the high geomagnetic anomaly and the high seismic velocity, so which shows that the asperities are characterized by low temperature. And also, the southwest of the epicenter is characterized by low geomagnetic anomaly and low seismic velocity, which may imply that high temperature anomaly here have acted as a barrier for seismic rupture propagation, so it didn't propagate to southwest in this case. Thank you.